Okay, today we are going to move into the second section of Chapter 8, and finally, I've been talking about these since Algebra 1. We are going to figure out what imaginary numbers are. So there's going to be a lot of reading today, so bear with me. It's going to feel maybe like a history lesson, but it is some interesting information, and then we'll look at the key concept of imaginary numbers. So in our introduction, it says, in the past, you have not been able to solve some quadratic equations like x squared plus 4 equals 0 or x squared plus 1 equals 0 because there are no real numbers that you can square to get a negative answer. To solve this issue, mathematicians created a new expanded number system based on one new number. However, this was not the first time mathematicians had invented new numbers. To read about other inventions, we are going to look at the historical note after we do our warm-up problem 63. So in this lesson, we are going to learn about imaginary numbers and how we are going to use them to solve equations that we were previously unable to solve. So as our warm-up, we are going to look at the equation x squared equals 2. So if we're going to solve this equation, question A says, how do you undo squaring a number? Everyone is going to tell me that you square root. Okay, to undo a square, we are going to take the square root. So it says on B, when you solve x squared equals 2, how many solutions are we going to expect to get? Okay, well, a lot of people like to just think one, but we need to remember that we are going to get two solutions. Okay, yes, we can't come up with the solution on the top of our head, but if we look at, for instance, x squared equals 4, okay, what are the solutions to x squared equals 4? X could equal 2, but x could also equal negative 2. So that's where the plus or minus comes into play. So on C then, it says how many x-intercepts would the graph of y equals x squared minus 2 have? Now please note that this function is directly related to x squared equals 2 because they moved the 2 over with the x squared. So when we're talking about x-intercepts, we automatically think, okay, let's replace the y with 0. So if we do 0 equals x squared minus 2, and then we're going to move the 2 back over by adding it, so we have 2 equals x squared. If I solve this, I am going to get how many solutions? We said 2 solutions, so really these solutions are x-intercepts. So 2 x-intercepts are going to result when we take the square root. In an equation, when you take the square root, you consider the plus or minus case. So now let's go ahead on D and solve the equation x squared equals 2. And it says to write it as both exact radical, remember another word for radical is root, and decimal approximations. So when I'm going to solve x squared equals 2, okay, we've said that you square root both sides to undo the square, but when I square root a number, I need to consider my plus or minus case. So x equals plus or minus the square root of 2. This is exact radical form. Positive square root 2, negative square root 2. But then when we go to the decimal approximations and take our calculator, okay, if we do square root 2, you're going to get a long never-ending decimal. And when we round it to the nearest hundredth, it's going to be plus or minus 1.41. So that is the decimal approximation. So exact radical form, decimal approximation. Okay, so getting us to think about square rooting because that is really at the base of imaginary numbers. But here's our first kind of historical note, not on imaginary numbers, but irrational numbers. Okay, so it says, in ancient Greece, people believed that all numbers could be written as fractions of whole numbers, what are now considered rational numbers. Many individuals realized that later some numbers could not be written as fractions, such as the square root of 2. And these individuals challenged accepted beliefs. Some of the people who challenged beliefs were exiled or outright killed by these challenges. I tell you, mathematics can get pretty dangerous and controversial. Okay, second paragraph. The Greeks knew that for 1 unit square, so if we have a square and each side is the length of 1, okay, then the length of the diagonal, which I'm going to draw in red, the length of the diagonal squared yielded 2. Okay, and we now know Pythagorean theorem saying in a right triangle, leg 1 plus leg 2 is going to equal the hypotenuse squared. Okay, so we can call that c squared. When it was shown that no rational number could do that, the existence of what we call irrational numbers was accepted, and symbols like the square root of 2 were invented to represent them. Okay? Because we know 1 squared plus 1 squared equals 2, but that is not the length of the hypotenuse. Okay? So we saw that then c squared is 2, but we care about c. So what is c? The square root of 2, which cannot be written as a decimal or a fraction. Okay, so it's a never-ending repeating or not repeating decimal that we have to round. So this square root 2 is considered irrational. So the problem, like x squared equals 3, also doesn't have rational solutions. Fractions would never work exactly. The rational solution on the calculator and computers provided are truly only approximations. The only way that we can represent the exact answer to this equation right here is by plus or minus root 3. We have to leave the root in there or else we would be rounding decimals. So in 64, it says mathematicians throughout history have resisted the idea that some equations may not be solvable. Still, it makes sense that x squared plus 1 cannot be solved because the graph, if we were to graph this, it has no x-intercepts, and that makes sense because this is a vertical shift of what? Plus 1. So what would the parabola look like? The parabola would look like this. There's a rough sketch. So we can see that x squared plus 1 equaling 0 isn't going to have any x-intercepts because it doesn't ever touch the x-axis. So why or how could we anticipate that without the graph? Because some of us don't like to graph. Well, if we just start solving it by hand, we're first going to move the 1 over to the other side. And then if we square root both sides, we get x equals plus or minus the square root of negative 1. But what do we know? We know that we cannot square root negatives. So in this case, we say no real, and that word is going to be key from now on. No real solutions. So now you're probably catching on to where this imaginary is going to come in. So this is how we would have responded up to this point. No real solutions exist for the equation that we're looking at because we cannot square root a negative. Okay? So the moral of the story is we now are going to call this type of solution something else when there's a negative underneath the square root. So now for our second of two historical notes, okay, it says, in some ways, each person's math education parallels the history of mathematical discovery. When you were much younger, if you were asked how many times does 3 go into 8, or what is 8 divided by 3, you might have said 3 doesn't go into 8. But then you learned numbers other than whole numbers, and the question did have an answer. Later, if you were asked what number squared makes 5, you may say no number squared makes 5. But then you learned numbers other than rational numbers, and you could answer that question. What is the answer? It's the square root of 5, because the square root of 5 squared is like root 5 times root 5, which any root times itself pops out what's underneath, okay? But that is a very upper level type idea. So similarly, this is the second paragraph, until about 500 years ago, the answer to the question, what number squared makes negative 1, was no number squared makes negative 1. Then something remarkable happened. An Italian mathematician named Bombelli used a formula for finding roots of third-degree polynomials. Okay, that's something we studied in section 1 of chapter 8. X-intercepts of third-degree polynomials, meaning that there's 3 factors or repeated roots. Okay, within the formula, the square root or was a square root. And when he applied the formula to a particular equation, the number under the square root came out negative. And we know that's no good. We just saw it on the first page. Instead of giving up, he had a brilliant idea. He had already figured out that the equation had a solution, so he decided what would happen if he pretended that there was a number that he could square to make a negative. Remarkably, he was able to continue the calculation, and eventually the imaginary number disappeared from the solution. More importantly, the resulting answer worked. It solved his original equation. So this led to the acceptance of what we now know today as imaginary numbers. The name stuck, and mathematicians became convinced that all quadratic equations do have solutions, okay? Of course, in some situations, you will only be interested in the real number solutions, meaning x-intercepts. That is solutions that don't have an imaginary part. But for this section, we're going to look at the solutions in which there is an imaginary part. So this is definitely about to be the key idea of the day. Key idea. Okay, so it says in the 1500s, the Italian mathematician Raphael Bombelli invented the imaginary number, which is the square root of -1. If anyone asks you what is the imaginary number, it is the square root of -1, okay, which is now called I. So, key idea. I is equivalent to the square root of -1 in mathematics. Okay, now what would happen if I square both sides of this equation? If I square both sides of this equation, I get I squared equals what is a square root times itself? Root of -1 times root of -1. When I take a root times itself, what pops out? The value underneath. So I squared is -1. That is huge. I squared is -1. So you need to memorize these two ideas until you really kind of get the hang of it. After this invention, it became possible to find solutions for equations like x squared plus 1 equals 0. And those solutions would be I and -I. Okay, so the value, if we're looking at what is the square root of -16, well, now what we're going to do is we're going to break it apart. And if you notice, -16 can be written as -1 times 16. Well, what did we just say that -1 was equivalent to? I squared. -1 is equivalent to I squared. So if you notice, they replaced -1 with I squared, and then now they're going to evaluate the square root of each part, because multiplication occurs under the square root. So the square root of 16 is 4, and what is the square root of anything squared? Itself. So the square root of I squared is I. That's important. The square root of I squared is I. So that's where they got the I. So the moral of the story is the square root of -16 is 4I. Very kind of interesting, but it's just like a puzzle in my mind until you get used to it. So let's practice, okay? This is what you'd be expected to do kind of on your own in a few days. So it says, let's rewrite each of the following expressions. So the first thing that I'm going to do is when I see the negative, I'm going to rewrite it as the square root of the positive number times -1. Okay? Now we know that this can be looked at in two ways, and I want to give you both ways. You can look at it as the square root of 4, and then what is the equivalent of -1? It's I squared. But you could also look at it as the square root of 4 times the square root of -1, because when you multiply square roots, you just simply multiply what's underneath each root and combine them. So if you like this second way, okay, then we can see, I'll just follow below it, what is the square root of -1? I said to memorize that it is I. So right away, we can put an I in place of the entire square root of -1. So there's no more square root. And then what's the square root of 4? It is 2. So 2I. Now, if we continued with this path, okay, and we looked at what is the square root of 4? 2. What's the square root of I squared? I. So either way, you're going to get to the same answer, but I want to show you both ways. So 2i is what I would expect. That is equivalent to the square root of -4. Now on this second one, okay, there is no square roots, but it's just saying let's use our normal mathematics, and you can treat I like a variable, and it says 2i times 3i. So this is straight multiplication, and we can use the commutative property to say 2 times 3 times I, because there's no addition, so we can reorder. So 2 times 3 we're going to treat as normal, which is 6, and what is I times I? Well, just like x times x, it's I squared, or x squared. Treat it like a variable. Now, what did we say to memorize? We said to memorize that I squared can be replaced completely with -1. It's like substitution. So 6 times, I'm going to replace I squared with -1, and we get -6. So 2i times 3i is equivalent to -6. All right, continuing on. We have some multiplication, but I want to write it out as 2i times 2i times -5i. So what I'm going to do is take my numbers, because it's straight multiplication, and I'm going to do 2 times 2 is 4, 4 times -5 is -20, and then I times I is I cubed. Okay, however, do I really want I cubed? I want I squared. So I'm going to go ahead and take these first two i's and combine them, but I'm going to leave the second I, or the third I, by itself. Okay, and you'll get a hang of these tricks. So then from here, we think, okay, well, we still have -20, and what is I squared? I squared is equivalent to -1. And then can we do anything with I? Sure, we could replace it with the square root of -1, but that isn't going to take us anywhere. It's going to take us in circles. So we want to show that this isn't going to be an imaginary answer. So we're going to leave that I on the end alone. So -20 times -1 is 20, and then we have one more I. So 20i is equivalent to what we started with. Okay. And finally, now we're back to like letter A, so maybe you try this one on your own. But we have the square root of -25, and we have the square root of -1. I'm taking this this approach right here. So then, not -25. It should be the square root of 25 times the square root of -1, because -1 times 25 gets us back to the number underneath. So what's the square root of 25? 5. What's the square root of -1? I. So basically, when you're taking the square root of a negative number, you take the square root of the positive value, and then you tack an I on at the end. Hopefully you're noticing that pattern, because you do want to get quick with these. All right. So the final problem that we're going to look at today is looking at graphing a function when there are no x-intercepts, and then what that's going to mean in terms of imaginary numbers. So we are asked to graph x squared minus 4x plus 5. And when you complete the square, I'm going to go ahead and tell you that completing the square will get you this as your graphing form. So y equals x minus 2 quantity squared plus 1. Okay, so this is graphing form of the function they gave us. So that tells me that my vertex is going to be at +2, +1. So over 2, up 1 is my vertex. And then I am going to go ahead and see that there is no stretch factor out front. There is no a value besides 1. So I can go out 1, up 1. And then I can go out 2, up 4. This is a good review of our knowledge of the quadratic parent function. And here is my graph. My parabola. Okay, so it says, does the graph on A cross the x-axis? So in other words, if I were to find those x-intercepts by solving this equation, is it going to have real solutions? And the answer is No, it does not cross the x-axis, so there would be no real solutions. But what do you think there is going to be? There are going to be imaginary solutions. So what we want to do is use the quadratic formula to figure out where we're going to see this imaginary solution take place. So this is a good review of the quadratic formula. So we have x equals the opposite of b is 4 plus or minus the square root of negative 4 quantity squared minus 4 times a is 1 times c is 5. All of this is over 2 times 1. So then we have 4 plus or minus the square root of 16 minus 20. Okay, 16 minus 20 is negative 4 over 2. So at this point, okay, up to this day in Algebra 2, we would say that there are no real solutions, which we obviously knew that, no real solutions. Okay, but now through this chapter, we can say that there are imaginary solutions when you see the negative under the square root. So at this point, we could continue on now, and we can say that what is the imaginary solutions going to look like? You're going to keep your 4 plus or minus, but what is the square root of negative 4? Well, the square root of negative 4 was given to us on problem A of 65, and the square root of negative 4 is equivalent to 2i. And we're still going to divide it by 2. Okay? So now we can do some simplifying because 4 and 2 are divisible by 2. So 4 divided by 2 is 2. And then 2 divided by 2 is 1. So I'm not going to put a 1, but I do need to keep the I. So this is the solution to the equation. So the x-intercepts are imaginary, hence why you can't see them when it is graphed. Okay, but this is the imaginary solution. When you don't get real solutions, you from now on need to give the imaginary solution. Okay, so on C it says any real number plus or minus a multiple of I, like each solution that we got on problem B, is called a complex number. So 2 plus I is complex. 2 minus I is complex. Okay, if I say 3 plus 2i, that is complex. So you have your real component, okay, which they said real number, and then you have your imaginary component, which is a multiple of I, but we call that the imaginary component. So here's my imaginary component, here's my real component. So what we want to do is check one of our solutions from part B to see what happens when we plug it in to our original equation that we were given. Because remember, a solution, whether it's real or imaginary, should make the equation true. So let's go ahead and look at, let's see, so does 0, because remember we were actually, solving this equation right here. So does 0 equal 3 plus 2i? Okay, that is my solution. And we're going to check, not 3 plus 2i. I'm throwing myself off because that was just an example. Okay, let's give ourselves some room. So does 0 equal 2, let's just check the plus, 2 plus I squared minus 4 times 2 plus I, and then plus 5. So when I take 2 plus I, when I take a complex number squared, I have to FOIL. I have to do double distributing. So I'm thinking of 2 plus I times 2 plus I. So 2 times 2 is 4, and then I have 2i and 2i, so I have 4i, and then I times I is I squared. And then I have distribute negative 8, and then negative 4 plus 5. Okay, well, we see that what is I? I is equivalent to, what am I doing here? I'm just making mistakes left and right. that should be an I. I can't read my own handwriting. So when that is an I, okay, this should be negative 4I. Okay, that makes me feel better because now when I simplify, I see a 4I. Whoops. I see a 4I and a negative 4I. We want those to cross out. What do I know I squared is equivalent to? You should have that memorized in this lesson. It's equivalent to negative 1. So now I'm going to substitute in that equivalence. So plus negative 1, and then I have minus 8 plus 5. So we have 4 plus negative 1 is 3. 3 minus 8 is negative 5. Negative 5 plus 5 is 0. So we see that this imaginary number is indeed a solution because it makes the equation up here true. Okay, so I know that was a lot today, but if there's one thing that you take away, you need to get memorized the following: that I is equivalent to the square root of negative 1, and I squared is equivalent to negative 1. Okay, these need to be memorized in order to be successful in working with imaginary values. Good job today. You have half the homework to do today, and then the next half of 821 will be assigned tomorrow.